Well, I changed my last name from Nygaard to Dovland some 10 years ago. But then I decided that as a mathematician, I should continue to be Olav Nygaard. Otherwise, I would have no publications. And then so we are equivalent.
Okay.
Yeah.
What will speak about them?
Yes. I know how to do that. This is the Banach group in Kristiansand, Norway. I think we are the only in Norway doing only Banach Spaces. It's from the left, André Ostrak from Tartu, and that's me. Trond Abrahamsen, André Martini, and Vegard Lima. Vegard Lima is the son of Oswald Lima, who you may know. Yeah, we have collaborating work with Murcia, Granada, a lot with Tartu, and it used to be also with Berlin, a little with Paris and with Besançon, and also with Prague. So what I'm saying now is, I think I like to present the Kristiansand group more than just presenting my work. We need to do some definitions. X is always a Banach space, and most of the time it will be real. Whenever I write S, it's a slice of the unit ball. So you intersect the unit ball with a half plane. And the interesting thing is when the half plane is quite near to the boundary. Then Sn means a convex combination of n slices. I think you can imagine what that is. You take some t between 0 and 1, then you take t times one slice plus 1 minus t times the other slice, and you have the combination of 2 slices, and then you can do it for 3 slices, and so on. And whenever I write U, I mean a non-empty, relatively weakly open subset of the unit ball. So it's the intersection of a weak open set with the unit ball. And now I can wonder what happened with these kind of sets. There is an important lemma due to Bauguin. It's much more general than this, but it says that whenever you have such a U, which I remind you is a relatively weakly open subset of the unit ball, then it contains some combination of slices. And then there are some definitions. Maybe I should draw. So you have the unit ball, part of it, and then you cut it by a slice. You could cut like that, and now you see that the slice is very small, and if you cut like this, you see that the slice is very big. And we say that the space has the local diameter 2 property if all the slices reminds you of that. So the diameter is 2 always. Now I can cut the unit ball by some weakly open set. And they go to infinity in a lot of directions. And this is a particular case of a relatively weakly open set. And the diameter 2 property itself is that all such sets have diameter 2. And then the strong diameter 2 property is that if every convex combination of slices should have diameter 2. And now you see that the diameter 2 implies the local diameter 2, simply because they are particular cases. And by Bauguin's lemma, the strong diameter 2 implies the diameter 2. And for a long time, it was unclear to me whether they are at all different. At this time, it's a terrible time to give a talk because everyone is hungry. Everyone just wait for the food to come. But let us just think, what is a nice definition? I have tried many definitions, and most of the time I give a definition and I can prove only one result, and most of the time no result at all. So the good with this definition was that it turned out to be easy to understand and not too difficult to find theorems. So let's go back to 2013. What did we know? We knew that spaces with a Daugavet property have the strong diameter 2 property. I learned from Dirk. He is here. Then, together with Dirk, we proved that uniform algebras have the diameter 2 property. And if one looks into the proof, we really proved that it has the strong diameter 2 property. That was 2001. And then Lopez Perez and Miguel Martin proved that in particular M-embedded spaces will have the will have the diameter 2 property. And again, if one looks thoroughly, one will see that it's the strong diameter 2 property. In the same paper was proven that if you take an L1 sum or an L infinity sum, then you will not lose the strong diameter 2 property. It's implicit in that paper. So that was what we knew when formulating the three definitions. And then the most interesting property we discovered is that the local diameter 2 property and the diameter 2 property is stable with respect to any p sum. So not only L1 and L infinity. That's what we knew. But remember, we didn't know whether the three properties indeed are the same. We published the first paper without knowing that. We just had to formulate the definitions, prove some results, and asking the question. And then it went very quickly. So we had to add in proof that in Tartu, they had proven that if you take C0, which has the strong diameter 2 property, because it's M-embedded, for example, then if you form the 2 sum of C0 with itself, it loses the strong diameter 2 property, but as I told you, it keeps the other diameter 2 properties. Thus, the strong diameter 2 property is stronger. And independently, they proved the same in Granada. So, those are different. And it turned out that it's only the 1 and the infinity sum that keeps the strong diameter 2 property. You always ruin it by taking p sums between 1 and infinity. Then, in Granada 2015, they proved that whenever you have a space with a copy of C0, it can be equivalently renormed to have the weakest of this diameter 2 property, but not the diameter 2 property itself. Yeah, Abraham is here. Yeah. I guess that was one of your first papers. It's difficult. Yeah, and then we started to think about diameter 2 property passing down to subspaces. And first we thought that, okay, complemented subspaces, locally complemented subspaces, and then it turned out that that was not enough. When a subspace is locally one-complemented, it means that there are local retractions. But the point is that those local retractions have to be almost isometric. And then all these properties passes down to subspaces. Then we learned of a new result, which was an old result. It's from Deville and Godefroy. And if one reads their paper in our language, it says that X has the strong diameter 2 property if and only if the dual space is so-called octahedral. The definition is here. It means that there is some kind of L1 structure in the dual. So then there's a dual characterization of the strong diameter 2 property. And now, of course, the immediate question is, are there octahedrality properties in X star equivalent to the other diameter 2 properties? Yeah. They found the properties in Tartu just after. So it is to weaken octahedrality in the right way, and then you get equivalent formulations. Then we looked for, okay, how to find properties that imply diameter 2 properties. I wasn't very much involved in that, but Trond Abrahamsen and Vegard Lima worked with almost square spaces and saw that they implied strong diameter 2 and much more. Then we start to think about something. What about Banach spaces where all the subspaces are also diameter 2 spaces? And to me, the only example are the non-reflexive M-embedded spaces. So that's something one could look at. Probably there are other spaces, but I don't know. Then another interesting question is, if you look at this drawing, you get an idea that the unit ball has to be quite square. If you can always cut and get diameter 2. But remember, this is a two-dimensional picture, and in infinitely many dimensions, a lot of things can happen. Yeah, I'll come back to that. And then it became very popular to look at free spaces after this paper by Godefroy and Calton, I think around 2005. And what about free spaces and Lipschitz spaces or various metric spaces? Then you could have a lot of examples. I'll say a little more later. It will be very little about that, because I realized that if I start to say anything about it, then it would be another half an hour. So, as I saw that we think that it implies some kind of squareness when all the slices have diameter 2. But remember, even the most extreme of them, the M-embedded spaces, which have the property that all subspaces are M-embedded spaces, so that all subspaces are strong diameter 2 property spaces. There are strictly convex examples of such ones. And also we should note that there are no points of continuity on the unit sphere when X has the local diameter 2 property, because then you need to have slices of arbitrary small diameter. Maybe another drawing. So, if we think of a line like this, then Radon-Nikodym property is on that side. We have reflexive spaces, we have Hilbert spaces, and then we have the in-between spaces, and then we have these big slice spaces on that end, and we have M-embedded spaces like C0 are on that side. And if we now combine, and we put on convexity of the norm, how is it then possible to act in this region? Yeah. If you haven't seen the definition of midpoint locally uniformly rotund norm, then just know that this is something quite a bit stronger than strict convexity. And we proved 9 years ago that it's possible to renorm C01 in such a way that you have both diameter 2 property and M-Lure norm. And yeah, you see that remark. Open question. Is it possible to have M-Lure and SD2P? If I should guess, I would guess it's not. I don't know. And you can weaken this M-Lure property a little so that you get the weak M-Lure norm. And from 2 years ago, well, 2024 is in fact 1 year ago, but it took a long time until the paper was published, so it's 3 or 4 years ago. It's also possible to renorm L1 to have a diameter 2 space, which is weakly M-Lure. But that renorming is not SD2P, and it is not M-Lure. So the question is then, can you push it even further? I guess not, but I don't know. And there's an old result, and I don't remember who was the one who found it. It may have been Dismier, that in the fourth dual is never strictly convex, well, except in trivial cases. So, if you start out with some of the diameter 2 properties, can you still have the bidual strictly convex? Remember, the fourth dual can never be, the third dual can be, but it's hard to be. Then what about the second dual? So what we know about that, this is a question posed by Trojansky. So what we proved is that the strong diameter 2 property, then you can never have a strictly convex bidual. But the rest of the question is still open. And I wouldn't bet much on what is the right answer here. Maybe it's possible. Then a little at the very end. I don't know if you have worked with Lipschitz functions or free spaces, but you take a metric space, you fix one point that you call 0, and then you take all the Lipschitz functions defined on that metric space with the property that in that fixed point, the value is 0. And then you get the Lipschitz dual, or the Lipschitz space, the lip null over M. And then what we know is that they have a very strong tendency of being diameter 2 spaces. In fact, Johan Langemetz and Abraham Rueda-Soka proved that if M is unbounded or not uniformly discrete, then this space has the strong diameter 2 property and even something stronger. So this is the place to look for diameter 2 properties. So there's a hunting plan. Try to characterize the metric spaces so that you get exactly LD2P, exactly D2P, exactly SD2P. And I'm sure much more is known, but what is known by now is that the Tartu group has characterized the metric spaces that gives you LD2P and the metric spaces that gives you exactly SD2P. Needless to say, these characterizations of M are not too easy, but at least it's possible to characterize and then construct metric spaces that gives you exactly the property that you want to have. And in some sense, although I have nothing against renormings, but the nice thing here is that you really construct what you need to start out with, and you get the space with the property that you want. And now let's have something to eat.